All right, let's get started for today. So we've started discussing about semiconductor lasers, and one of the things I mentioned in the class on Wednesday was that we're going to find the gain spectrum of a semiconductor laser, and we'll find that it's actually very similar to what we have seen already for atomic systems. It has the wavelength dependence, it has the spontaneous emission lifetime dependence, and instead of the line shape, we'll have what we're going to call as this optical joint density of states that represents both light and the matter of the semiconductor, or the atoms of the semiconductor. It will have the band gap of the semiconductor and some other details. And the population inversion will be the population of electrons in the conduction band manifold and the valence band manifold, and the difference between them. So that's the main change. And today what we're going to do is kind of look at how this comes about, because much of the differences between a semiconductor laser and traditional solid-state laser based on atomic systems is in these details, primarily in the joint density of states, or the optical joint density of states, and the population inversion term. So we are going to look at both of them, and then apply the same techniques earlier of writing down the rate equation, get spontaneous emission, stimulated, and absorption, and we'll see that how, once we understand this whole picture, you can turn the semiconductor system around and either make a laser with it, or a LED with it, or a photodetector, or a solar cell. It's all a play on these coefficients here. So which device you wish to make depends on how you design these terms inside here. So that's why we're going to spend a little bit of time understanding how the gain spectrum, or it's actually, we're going to see is the inverse of the absorption spectrum of a semiconductor, how that comes about. So towards the very end of the class last time, what I mentioned is we were looking at the problem of an electron in a solid or in a semiconductor crystal, where you have a perfect arrangement, perfectly periodic arrangement of atoms. And because of that, what I mentioned was that the electron energy, now I'm going to sketch it in this manner. So the electron energy, instead of drawing them as discrete lines here, I'm going to draw it as a parabola, as a function of the wave vector k, which is 2 pi by the wavelength of that electron. Why am I doing that? Because we said that the energy of the electron in what is now this manifold of energies here, a bunch of energies here, we're going to call as the conduction band, that has become equal to the energy at the edge, or the minima, plus the kinetic energy. So that's the potential energy plus the kinetic energy. And the kinetic energy is, from de Broglie relation, the momentum of a particle is h bar times k. This is one of the fundamental results of quantum mechanics. Momentum is h bar by times k, be it an electron or a photon, same thing. So it's the h bar times k. So the momentum squared by mass is the h square k square by twice mass is the kinetic energy, except now here, because of the fact that it's in a crystal and the details of the periodic potential, instead of a flat potential in space, it has a periodic potential. And that part is kind of absorbed in the fact that inside a semiconductor, instead of the free electron mass, we have a slightly different effective mass, right? The conduction band edge effective mass. This is the effective mass of conduction band for semiconductor. Now, typically the effective mass would be smaller than the free electron mass. If you look at gallium arsenide, it would be 0.06. So it's 6% of it's very light in some senses. It behaves very lightly. For some other, so as the band gap increases, the effective mass kind of increases as well for the conduction band, and it approaches the band gap. It approaches the free electron mass, but for most semiconductors, it's smaller than the free electron mass. So, for example, in gallium nitride, which is a relatively large band gap semiconductor, that is about 0.2. So it's 1/5 of the free electron mass. Why it changes in the way with band gap and all, that's a very simple application of perturbation theory and such things, but we are not covering it here. Okay. Similarly, you have the valence band, and the top of the valence band is, we are going to label it as E sub V. C is for conduction and V is for valence band. The top of the valence band is E sub V, and now you also have a manifold of, or bunch of energies allowed here. But then if I choose an electron here, I'm going to say that it has this much potential energy, and the way it's drawn here is, you see, it's flipped, and this much is its kinetic energy. Similarly, if I choose a particle here, its potential energy is the minimum here plus this. Here it's EV minus this. Mainly because you can see that when we're going to recombine, if an electron state here falls into an empty state here, let's say, then it's going to emit a photon, which is what we are after really. And then the total energy then will be, the minimum and the maximum here, which is called the band gap of the semiconductor, plus the kinetic energy of electron plus the kinetic energy of this state here. So that's the total energy will be like that. So we can write that the conduction band state, I'm going to label it very similar to our atomic state systems as E2. Let's call it E2. That's what we have called earlier for our atomic systems, and I'm looking at this figure here at this point. So this is E2. Let's choose a state here. And so E2, therefore, will be equal to the conduction band minima plus this amount of kinetic energy here. And similarly, the ground state I'm going to choose as this one. That's EV. So this state here is E1. Okay. That state is E1, E2, and E1 I'll write it as E valence band edge minus this much, and that is minus h square. And I'm going to just write it as this right now, and let me explain why I'm writing it in this way. Okay, so the as you can see, the curvature of this parabola, if I plot it versus k, the curvature is kind of this related to this coefficient here, right? How strongly is it curved? If the mass is very light, it curves very sharply. If the mass is heavy, it curves relatively, lightly. So this is a heavier band. That's the name used. It's a heavier band. This is a light band, for example. And these, from detailed quantum mechanical calculations, one can calculate out exactly how much is the effective mass of holes or valence band. So this is effective mass of holes. That's effective mass of electrons. So you can kind of calculate those things out. And these parameters have been measured to great accuracy with experiments and such things here. Typically, the hole effective mass is heavier than the electron effective mass, and it could be more like points. So for example, in gallium arsenide, this is 0.06 times the free electron mass, whereas this is more like 0.2 or something like that. So it's heavier. It's maybe 3 times heavier or something like that. And okay, so those are the two states. Now the photon, on the other hand, also has its own momentum, right? So if an electron from this band recombines or falls into this state and emits a photon, two things, actually many things must be conserved in any such process. The energy must be conserved, the momentum must be conserved, and angular momentum also must be conserved. All the conservation laws should kick in, and it should restrict which states are allowed to make a transition like this. So the first thing I want to get out of the way is angular momentum. We haven't discussed too much about it, but what is the angular momentum of a photon, one single photon? Anybody has an idea? So it's a difficult question if you don't know about it. It's not easy to guess, right? So yeah. Yep.
Is it ml h bar?
Yeah. So it's basically h bar. Just h Planck's constant. That's the meaning of Planck's constant if you look at the units. That's the angular momentum of a photon. And so meaning if you have a right circular polarized photon, it has kind of that much angular momentum, and it can mechanically twist if it interacts with particles. And that's how liquid crystal display LCD screens are made, because it has this angular momentum, and you can have polarization sensitive kind of connection and all that. So that part I want to get out of the way because I don't want to get into the details of it, except just saying that a band here, which is the valence band, has a certain angular momentum because of spins and all these things that come along and create it. And the conduction band has a different angular momentum, and the difference in angular momenta between these two is exactly h bar. It's exactly one quanta of angular momentum. So that ensures that if I have a transition from the conduction band into the valence band, I'll, whatever particle comes out of it will have an angular momentum of h bar. So that conservation, you're guaranteed. Energy conservation is very trivial now. You can see E2 minus E1 must be equal to the photon energy. That's very simple. So let's write that down. E2 minus E1 must be equal to the photon energy h nu. So that's the energy conservation. And the third thing is the momentum conservation. And the momentum conservation is what restricts what we're going to call as a vertical transition. In the k space for electrons, the transition will be for an electron with this much k and a valence band state of the same k. They'll be exactly the same. When I say exactly, it's somewhat of an approximate relation because, see, if the momentum, or if the k of the electron state was ke, let's say, and k of the whole state was k sub h, let's say, then one expects that h bar times k electron, it has a direction as well, momentum. So x bar times k whole should be equal to h bar times k of the photon that comes out. Let's write k sub nu, or the photon that is emitted. So it will have its own k of the photon. Right? And the k of photon is 2 pi by its wavelength, and then the direction is the direction in which that photon is going. Right? So that's the meaning of that. Now if you do the numbers, you will see that the k is for electrons and for holes in states. These are typically of the order of a lattice, a fraction of a lattice constant. Lattice constant meaning if you have the atoms in the crystal arranged in a periodic fashion, and the electron wave is going through, then the electron and the hole k vectors are of the order of pi over the lattice constant times maybe a factor of maybe 0.1 or something like that. But that's order of magnitude. It's just order of magnitude. And a lattice constant, how close are the atoms in a semiconductor crystal, is typically in 3 or 5 angstrom. This is angstroms, 10 to the minus 10 meters. Whereas the k of the photon, I think you can, k of the photon, k nu, is 2 pi by the wavelength of the photon. Right? And the wavelength of the photon, if you have a visible light, what's the wavelength typically? Order of magnitude. So maybe, I don't know, a few hundred nanometers, right? IR would be in a micron or so, right? So we are saying this is maybe a micron or a few hundred nanometers or something like that. So, and whereas this is in angstroms, so you can see right away, and it's sitting in the denominator, that the k of the electron or the hole is actually way larger than the k of the photon. Right? The momentum of the electron or the hole is way larger than the momentum of the photon, which is why it's actually, and in the book, they give some estimates like this could be 3 or 4 orders of magnitude smaller than that one, right? So as a result, we make a very nice approximation that that thing is actually kind of 0, and therefore, the transition. Let me just put it this way: this minus this, because we're going to transition from here to there. So therefore, the k of the electron and the k of the hole must be the same, which means in this picture of E versus K, it should be a vertical transition. There's no change laterally. So that's a momentum conservation, energy conservation. And I said that I'm not getting into detail of the angular momentum conservation, except that the photon, once it's emitted, takes away an angular momentum of h bar, and that comes, these two bands have an angular momentum difference of h bar. Any electron in this band and corresponding electron in that band will have a difference in angular momentum of h bar. So when it drops, you get that change. So I know, some of these, if you have seen this, it's great. If not, and you need further explanation, perhaps in the office hours or so, but you have a lot of these. If you haven't seen, I'm just giving a very rough summary of what has, century of physics behind it, and it confirmed experimentally and measured and understood very well now. Okay, so if you're fine with that, I think we are ready to we are good to go. Basically, that's all the trust we need. After that, we can from here on we can explain completely the joint density states and all the gain spectrum now. Okay, so that's the primary fundamental physical process that is going to be involved in absorption, emission, gain, stimulated emission, all that stuff is this process. Okay, any questions here? Well, okay, if not, let's look at how is the photon energy then related to the band gap and other things, right? So we can just take E2 minus E1 here, right? That's the photon energy. And so if I just take the, subtract the top line here, the bottom line from the top line, I get that E2 minus E1 is equal to the photon energy, h nu, is equal to, you get the conduction band minima minus the valence band maxima, EC minus EV, right? And then you see this thing actually adds, and physically you can see it must add because that's the kinetic energy of electrons, of holes. This plus the gap plus that is equal to the photon energy. And let me write it down in this way. ms of holes times k squared. And I hope, okay, it's clear that the k here, I've implicitly made the assumption here that the momentum conservation enforces a vertical transition. So the k of the electron is equal to the k of the hole. I've made that assumption already. And you see a new term kind of pops up here, which is 1 over the effective mass of electrons in the conduction band plus 1 over the effective mass of electrons in the valence band. And this is what is called as the reduced effective mass. We just define a new term, reduced effective mass. If you remember any of your classical mechanics of two masses moving and m1 and m2, and they have certain net momentum, so you go to the center of motion. So this is kind of the net mass of the whole thing in some sense. It's the same thing, right? Reduced effective mass. So and it has the information of both bands, the valence band and the conduction band, as you can see. So I'm going to just use that and write that down as m star of the reduced mass times k squared. Now what we are going to do is ask the okay, so let me complete this discussion. What is EC minus EV? That is the minimum of conduction band minus top of the valence band. That's the most characteristic thing about a semiconductor, is the energy gap of the semiconductor, or the band gap of the semiconductor. And so that is band gap plus h square k square by twice the reduced effective mass is equal to the photon energy that will be emitted upon that transition. So that's a very important relation. As you can see, it kind of ties in light and all the effects of matter are buried inside here. The fact that there is sitting in a crystal, it has a gap in the energy spectrum, and the fact that it's in a crystal, electrons are actually mobile. They form electron waves in the conduction valence band is buried inside here. So how mobile are they in some sense are also buried inside here. And now what we are going to do is so these are what is this equation really telling us? It's telling us that I have quite a number of states which will emit at a photon energy of h nu. Quite a number of states, as long as they follow this relation. So there are a lot of states with different values of k that could emit at this photon energy. There's not just one. I mean, in this picture it looks like there's only one here, but obviously you can see, flip it around here, there's another one here, the same photon energy, right? In fact, if you look at the band structure in a little more detail, it may kind of bend like that. There are some other details here. So you can actually have the same photon energy from many, many transitions here. Many, many transitions. And now what we're going to do is ask how many transitions, exactly how many, right? And that is the meaning of the density of states here. How many states with the same k, how many states with different k's will emit with the same photon energy? Does that make sense? And all these are capable of interacting, either absorbing or emitting that photon of that energy now. So we're going to look at the density of states, and that density of states is the joint density of states here that we are after. Right? That's the joint density of states. Right? It's like we have, if I find that that thing is 10 to the power 18 per centimeter cube, that means I have 10 to the power 18 individual, kind of atoms with exactly the same energy separation, and they're capable of interacting, just like we had it for atomic systems. There's a rough analogy to that. So we want to find how many states are available, okay, so let's do, is that clear? I mean, what we are doing here? It's not just one K, but many different Ks are allowed, and we want to find how many. Yeah.
So is this result true regardless of doping?
This, very good question. So this result is actually independent of doping. What we'll see is the doping is what's going to control, things like here, the occupation functions and all that. To first order, I mean, if you want to get into too much details, then even this, when you dope it very heavily, the tails, you develop band tails and all that. But we don't need to be concerned about that. At this point, yes, this result is independent of doping. Okay, so now the joint density of states here would let me write this equation in a slightly different way. So, well, not too different. It's just take one of the terms to the right, and we have that. And right away you can see that this is a net energy term, and it's a square, so it's positive, right? So there's a restriction on the number of K states, K starting from 0. So if we ask this, how many K states actually allow for a transition that has, this relationship. So then we can go back and ask the question, how many K states are there to start with, right? How many K states are allowed for the electrons to start with? And the number of K states that are allowed is really exactly the same question as number of modes that were allowed for a photon inside a box. Here we are going to use a semiconductor, PN diode, or a heterostructure, or whatever. So it's a box, and there are electrons inside there that can move along X, Y, Z, all three directions. Maybe I have a PN junction here. But now I have electron waves in this. Instead of photons, we have electron waves. So, and we know that the electron also has a wavelength, right? The electrons have wavelengths, and the wavelengths have to fit inside that box again, right? So we do the same sort of a discrete grid. We can say that moving along X, the electron Kx must follow, if I have an integer number of half wavelengths, it must follow that sort of a relation that it must, the way an integer number of half wavelengths must fit inside that box along the X direction. So I should have pi over Lx times some integer, similarly Ky. These are the macroscopic dimensions of the, it could be, if you built 100 micron or even a millimeter size PN diode, then these lengths are in millimeters of microns. It's a very large lengths. So yeah, but what we are really saying here is that the Ks must follow this. The Ks, not all Ks are really allowed, but only a discrete set. And if I go to the K space now for the electrons now and say that, well, if I have Kx, Ky, and Kz, then we get back our familiar sort of 3D. If my electrons are free to move in 3 dimensions here, then I get this discrete grid. And you get, by looking at it, we can write down our density of states now. So we have this, a grid with a separation of, pi over L. We have these little boxes of squares and all that. It's the same thing, right? Exactly the same as before. Same as we had done for photons. Yeah, that's the K-space grid now for electrons. But we kind of, I think we can borrow what we had developed there already. If we are in 3 dimensions, we can really write down by taking an analogy from what we had done before, that the density of states, physically, what does it mean? It means that if I go up to a certain K state, which is the surface, and then go out a little bit more, how many states fall inside that little shell in the K space. And that's really what we're asking here. How many K states are going to give you this photon energy? How many points fall inside that shell is really the answer. And it is the joint density of states here. And how many there are? So let's see. We have the surface area again of this 1/8 of a sphere. And the surface area is 4 pi k squared times dk. Surface area is 4 pi k squared. dk is the thickness if I go out along the k radius direction. And it's 1/8 of the sphere, so it's 1/8 of the whole thing. So that's the volume of this thin shell around. And each point here occupies a space which is volume of the cube, and that is pi over L. I'm assuming now that Lx, Ly, Lz all are same. It's a real cube. It's not a rectangle. But this result is actually robust. Even if one of them is longer than the other, this will still work out fine. You can actually check that here. And we will have pi over L whole cubed, which is the volume of a tiny cube in the K space here. So really, that is the density of states in K space. We want it in energy space, so we'll convert it now. Right? There's one more detail that in any state here, just like for photons, we had two polarizations. For any state here, for electrons, there can be two spins. There can be two spins. As the electrons are fermions, they are with a spin plus half or minus half. So we will add that spin factor in here. So allow for two possible spins, up and down spin here. And just to be clear, when you have a transition, you can have actually let me just mention it anyway. So if you have a transition and you have an up spin electron and a whole state, it must also have an up spin so that the angular momentum for photon is h bar. Otherwise, so generally you won't have a transition from up spin to down spin here. So that's a small little detail, but let's not worry about that at this point. So that's the density of states in K space per unit. So this is the total density of states, and you actually take over L cubed here. So that's the total density of states, and there's a volume sitting in the numerator. We want the volume, the density of states per unit volume, because you can make it larger or smaller. I don't want the total density. I want it per unit volume. So I divide the whole thing by volume. This is exactly the same as what we had done before. So I kind of take away that L cube, and that's really the final answer here. And the answer here would be, 4, 8, and 2. These things cancel out. You get k square dk over pi square. That's nice and simple answer for in the K space. So this is the density of states in K space, and as you can see, that we are really counting the number of states. Therefore, whether you do it in K space or in energy space, we should get the same total, the same density of states, whether you do it in K space or in energy space. So let me write this down in this way. This is the joint density of states in K space times dk. This must be exactly equal to the joint density of states if I move over to energy space, and energy of a photon happens to be h nu, and you can write it as h nu, but h is a constant, so we generally just write it as rho joint density of states of nu. So that's what we mean. So it's the same thing because there's a one-to-one correspondence between how many states here I can find with the same h nu difference. How many states in K space can I find, and how many photons are there in the once they emit? Right? So it's this one-to-one correspondence between them. So therefore I can write that, and I'm going to just say here that you have this relationship between K and nu. You can take a derivative, and convert this, and you can find your joint density of states here, right? So, so from here, for example, you will get that if I take, the K is 2 times reduced effective mass over h square, square root of that, right? And so I can take a derivative of this because I see there is a k squared dk, and I can split that into k times k dk. You can do it in any way you like, but this is one way. You've got a k, and you can take a derivative of the numerator, and you get like a k square. When you take a derivative, you get 2k dk, so you get a h square over m star reduced mass times k dk. From here, the 2's cancel, is equal to h times d nu, this, right? And you take this one, multiply it with this one, you're going to rearrange it, and you get k dk, and substitute it all there, and what you are going to end up with now is the joint density of states in the energy space, and this is the expression for it. And let me write that. So the joint density of states in the energy space, or the frequency space of photons, if you might, is so you have the reduced effective mass that we defined, Planck's constant squared, the whole thing 3/2 power. Then I have a square root of the photon energy minus the band gap. And that's all right. I mean, that's the joint density of states for that we are after. So the semiconductor system with all its atoms and electrons and arranged periodically, it gives you the gap, and it gives you this effective mass. And now, if you ask what photon energies am I able to extract out of the semiconductor, is it able to emit, and with what strength? This is the measure of it right now. So again, just repeating the same thing. So obviously, physically, it makes sense because you cannot emit anything smaller than the band gap. The photon energy has to be larger than the band gap, and that picture should be clear from here, right? I mean, that's the lowest energy photon you can emit, and once your energy becomes larger than the band gap, what it's saying is really that the joint density of states as a function of h nu it's 0, it starts at the band gap, right? And then it increases as a square root for a 3D semiconductor, three-dimensional material. It increases as a square root of it. So that's the physical meaning of it. And it means that as we go to higher and higher energies, if the photon energy is much larger than the gap, there are a lot more states. It can emit a lot more. So that's the physical meaning. And similarly, it can absorb a lot more too. So that's the physical meaning of it. And just like earlier we had talked about in the Planck's blackbody radiation formula, we had found the density of states of photons, but then you have to multiply it with what is the probability of this happening, right? And that's where we saw that there was another function that's kind of coming down with energy, either a Fermi-Dirac function or a Bose-Einstein function. Exactly in the same way here, the second factor in the gain spectrum is going to determine. So we already talked about the joint density of states. Now we're going to talk a little bit about these functions here. Now, instead of photons, we are now talking about occupation function of electrons in the bands. The electrons are fermions, and they follow the Fermi-Dirac distribution instead of photons, which follow the Bose-Einstein distribution, right? So what I want to say now is by playing with the semiconductor Fermi functions, what you can now what will now show is you can the total gain, the small signal gain is of some factors times the joint density of states times this Fc of E2 minus Fv of E1. And we're going to discuss this in some detail now, this function. But what I want to say now is I can do something to the Fermi functions by applying a voltage across a PN diode that will make this Fc minus Fv function something like this. As a function of energy, it will look something like that. It will be 1 for most energies till you hit a certain value here. And we'll see that this value will be controlled by a battery with a voltage V, 2 volts, so that will determine 2 volts. So 3 volts, it will determine that. So when I take a product of these two, I will get a gain spectrum which may look something like that. So that will be our gain spectrum in the end. So we're going to show that now. So once you make your semiconductor device, the density of states, the giant density of states is fixed. You can't change it anymore. But what you can change now is how much voltage you apply and batteries, and excitation, injection currents, and you can change this. If this value is way out here, then you don't have gain. Actually, we'll see that you will have loss. And that's a photodetector. It absorbs photons rather than emits. As you get closer, when you apply more and more voltage, I'm going to push this out, and finally you'll have a gain spectrum, something like that. So the gain spectrum of a semiconductor, if it's three-dimensional, is really very similar to the joint density of states with a little Fermi tail acting on it as well. So that's the main point we wanted to stress first. Okay, so let's look at the Fermi function details. Let me first write down the Fermi function for any electron of an energy E is 1 over e to the power e minus a certain characteristic Fermi energy, which is a measure of how many electrons there are. And so unlike photons, if I have, let's say this is some zero of energy, and I start pouring electrons in, one of the very important things about electrons is that not all of them want to stay at the bottom, right? They're there's an exclusion principle, which is why I can only fit 2 electrons, one with up and down here, one with up and down here, and therefore when I fill a bucket with of states with a lot of electrons, you immediately fill the states up, and then maximum energy rises very fast because they're not allowed to have more than 2 here, right? And this measure is the Fermi energy here, right? It's a completely quantum energy. You can freeze it to 0 Kelvin. This never goes away, right? It's from Pauli exclusion principle. That's the amount of certain quantum mechanical energy that it has, no matter whether you have thermal energy or not, it has this much energy just because they're fermions, right? And that thing is sitting here. That's the Fermi energy of a set of electrons, a bunch of electrons, right? Now, this is true in thermodynamic equilibrium. Just like we had for black body, the equilibrium is sitting here. What do I mean by that? I mean that if I have a semiconductor and I look at equilibrium, the semiconductor itself is sitting on maybe a package, and the package is sitting maybe in a room, and the room is at a certain temperature, so everything is at a certain temperature now, right? And so everything is under equilibrium, and the electrons in the semiconductor that are moving back and forth in the band, electrons in the conduction band or in the valence band, they are colliding with the lattice, with the atoms, they're colliding, so they are also in equilibrium with them, so there's no temperature difference effectively between them. So the electron has picked up the temperature of the electron distribution, has the characteristic imprint of the temperature of the surroundings inside there, under thermodynamic equilibrium, right? But the moment you apply a voltage across it, you completely pull it out of equilibrium, and that's where most of the interesting things happen now. So what we'll change this, what we'll say is the moment I apply a voltage to my electron system, for example there, to that system, and I'm going to be very precise now exactly what I mean by voltage and what, okay, let me actually sketch this. So I have the conduction band with a density of states that's, right, let me not try to write this. So here's the energy of the electron, and here's a conduction band, here's the valence band, and there's a bunch of states, electron states in the conduction band, there are a bunch of states in the valence band. And in a semiconductor laser diode, what we actually do is take a semiconductor and make a p-n junction out of it, right? We are going to have empty states in the p side and a filled states in the n side, right? So let's say this is p, or let me keep in p and n. And what do I mean by n? It's doped with extra electrons. So if I had an intrinsic semiconductor where I had no doping, the Fermi level EF would be somewhere maybe in the middle of the gap here. No, unimportant at this point exactly where it is, right? But if I dope it with electrons, or if I inject it with electrons externally, then what I do is I pull the Fermi level of the conduction band to a separate level. I mean, maybe inside the gap or close to the gap, and that level we are going to label as F sub n. This is the word for that. So this would be called as the Fermi level. It's an equilibrium property. And to characterize a non-equilibrium property, we're going to say that this is that's at least the name introduced by Bill Shockley, quasi-Fermi level. Quasi just means I'm out of equilibrium. But it's a very powerful concept, because if I can inject extra electrons and push the Fermi level away from here, and at the same time what I'm going to do is inject extra holes into the same region and pull the Fermi level from here, split out the Fermi level for holes. We're going to label as F sub p, n for electrons and p for holes. And how am I really physically changing these Fermi levels? What I do here is I physically make a contact, a metal contact, and I connect a battery. Now that's what is actually tweaking these things. So let's sketch this as Pn. So I'm going to explain this out a little bit. So let's say we ground one end and we connect a 1 volt or a 2 volt battery to the P side, and we ground one end. I think you know that it will try to flow a current, right? A battery wants to push a current through it, will inject carriers and all that. And when I form a contact, this is an ohmic contact, what it physically really means is I have connected the Fn, the quasi-Fermi level of all the electron population swirling around inside here to this terminal, whatever be it, whatever is potential. If it's at 0, the thing is at 0. Similarly, I have connected the F sub p, which is the quasi-Fermi level of all the holes that are floating around in the p region, to that terminal. And I can apply a voltage V across it, in which case that population of holes will have Q times V energy different from this population of electrons here. So I can split it. This Fn is controlled by this terminal, and Fp is controlled by that terminal. So I have two different populations of carriers. So I'm kind of individually controlling the conduction and valence band now, separately. This is a non-equilibrium situation. I know it's typically we cover this in a full semiconductor device course, but if you have seen p-n junctions, this is the physical meaning. One can imagine I have two different sets of electrons. One is just filled in the valence band, and one set which is just in the conduction band, and their net Fermi energies are different by the applied voltage across here. And to highlight that aspect, we write now that the Fermi level or the Fermi function, instead of being the same for both the conduction band and the valence band, we're going to write there are two Fermi functions but with slightly different Fermi levels, and that difference is equal to the battery voltage we apply on it, on the diode, laser diode, and we write it as 1 over conduction band electrons. We have used E2 as their energies over KT. This is for conduction band, and for valence band I've used E1 as the energies of the valence band electrons, and that's E1 minus the Fermi level of the valence band. We are calling it as F sub p over KT. And okay, so this is a somewhat of a, I would say, enormously simplifying concept, but it takes some time to appreciate how and understand what exactly are we saying. So just to summarize again, I have electrons in the conduction band and also electrons in the valence band. If I have an empty state, that is what we would call a hole. But let's just look at it as electrons in the valence band. I have a population here, effectively N1 in your atomic laser. I have a population here, effectively N2. But in a semiconductor laser system, what you have is, amazingly, you can control N2 and N1 independently. I mean, you don't have to start from here, put it there, and all that. You can inject extra electrons from outside, and that's the battery. The way you do that is with the battery. So when you inject electrons, when you pass a huge amount of current, you can effectively, independently control the N2 and N1 here, and then that control is captured in these two equations, which are the Fermi functions for the electron population and Fermi function for the whole population, or the valence band population. And in pictures now, if I were to sketch the Fermi functions, how will they look? Let's say I have applied a certain voltage. If I was at equilibrium, both, so this is energy, I'm plotting f of E, and I have valence band states here, conduction band states here, and the Fermi function or the Fermi level is maybe somewhere in the middle. So what it's saying is the occupation function of conduction band states at equilibrium, if I have not doped the semiconductor, it's 0 here and it's 1 here. All the states in this state are occupied, all the states here are 0. And that's the plot of the Fermi function. and this value is EF, the Fermi function. At EF, when E is equal to EF, this thing is half. So you have exactly half occupation and then nothing. Now, when I bring in the battery and I start looking at two different populations now. Okay. So when I bring in the battery, I split this function into two. And I have one for electrons, which would look, it will try to fill the electron states here. So that will look more like something like that. Maybe I pulled my Fn over there. And I have, so this is Fc of E2. And Fv of E1 is similarly, Fn will be 1, and then, well, that's the valence band edge. So we'll have something like this. And this value where it's half will be Fp. This difference is equal to the applied voltage across the battery. So you see now 0, 0. So very far out above the band edge, far from the conduction band edge, both states Fn and Fp said that my value of occupation function is 0 at very high energies. At very low energies, both say it's 1, but there is this little window inside here, little window within which Fc minus Fv is 1 minus 0 effectively. So what you get is a window of energies here. If I take this minus this, you get a window of energies within which all the business of a LED laser, semiconductor laser happens. All that stuff happens within that window. Everything else is irrelevant in this picture. And that's the function that sits out here in the gain function, Fc at E2 minus Fv at E1. That's what sits here. And your okay, so you can see from here that if I do not apply a voltage, I am actually not going to get gain. In fact, I will get, Fc at E2 minus Fv at E1 will be, let's say I look at a photon energy of, something larger than the gap, then I'll get basically a 0 minus 1. 0 minus 1, a state from here E2 minus a state from here E1. So I'll get a 0 minus 1. So I will get a negative gain coefficient, which is actually the absorption coefficient of the semiconductor. It's the same thing. This factor is minus 1. So the whole stuff sitting in front is still the absorption coefficient of the semiconductor. Then I start applying voltage, and what I start doing is I split the Fermi function kind of like that, and I make this part, I fill up the conduction bands here, I make this 1, and I empty out the valence band electrons, and I pull the Fp out here, and I make this 0, so I get a 1 minus 0. So that flips sign. It goes from minus 1 to plus 1 now. Fc, conduction band gets occupied, and valence band, you pull out electrons from here, and this becomes 0. So you get 1 minus 0. And that's when you actually have gain. And when I'm in equilibrium, then as I mentioned, this is 0, that's 1, so I get actually negative values. That's the plot of the gain spectrum. It's actually loss. But I think we understand if it's a negative value, your gain spectrum looks like e to the power gamma times a certain length. If this is negative, that's a loss. That's straightforward. But if you have that as positive, it becomes gain. And what we want to do now is look at this and apply it to the spontaneous and stimulated emission picture. And I think we're slightly out of time today, but what we'll do that in the next class on Monday. So please actually read up this part. If you have any questions, we'll have some office hours next week. We can discuss this aspect of it. But if we are comfortable with this picture, I think we are in a good spot to completely understand the semiconductor laser diode. So, okay, all right. So let's meet on Monday.